Hello, everyone. This week we will be discussing Chapter 8, which is all about solutions. Before we get started, I just wanted to give a brief update of what's going to be happening in the upcoming weeks. By Thursday or Friday, the exam number 2 scores will be up on Moodle, so make sure to check the Moodle page to see your exam score for number 2 exam. And if you have any questions or concerns about the grading or any of the answers, please feel free to email me. The second thing is that on next Monday, which will be the 20th, we'll have a quiz for Chapter 5. In preparation for that, since Chapter 5 included 3 pretty large sections that are on YouTube, I'll be holding online office hours and a review of Chapter 5 tomorrow. And I sent the email out about that with information on how to join the Zoom meeting. If you have any additional questions, please feel free to email me at any time. So we're going to go ahead and get started with our lecture. Okay, so Chapter 8 is all about solutions. And in Chapter 1, we talked about different types of mixtures. We can have homogeneous mixtures of molecules or atoms. These are mixtures where you cannot tell the individual components of the mixture from each other, or you can have a heterogeneous mixture where you can pick out the individual components of the mixture. A solution for our purposes is going to be a homogeneous mixture of molecules or atoms. And there are 2 components in every solution that we'll need to know. There'll be a solvent, and this is the substance that is present in larger quantity, and it will all be the same phase. So it'll be either a gas, a liquid, or a solid. Then we'll have a solute, and that's the substance present in a smaller quantity. The material that is dissolved in the solvent. And it may be in a different phase than a solution. So you can add a solid and dissolve the solid into liquid. And so, for example, this happens when you add sugar and water or salt and water. The water will be your solvent in liquid phase, and then the salt or the sugar would be your solute in the solid phase. And here I'm showing a representation of what a solution would be like. So we have a beaker. We'll just say this blue liquid is the solvent, and we'll say that's water. And then the solute are these little yellow dots, or the solid pieces. And both of these make up a solution. And so, for example, down here, we have CO2 gas that is dissolved in Coke syrup, which makes Coca-Cola. This is how we get soda. The CO2 makes it fizzy and makes those bubbles. So the solvent is going to be our liquid, which is the Coke syrup. The solute is going to be the CO2 gas. That's what we're adding to the liquid, and the solution is the liquid because there's more of that. So we'll just want to keep these definitions in mind as we continue through the lecture. So we have types of solutions. You can have more than one solute in a solution. So the example I gave before was adding salt or sugar to water, but air is actually a solution as well. And so air is made up of O2, oxygen, argon, carbon dioxide, water dissolved in N2 as a solvent. Air is O2, argon, and carbon dioxide are some of the components. And then if you have water dissolved in nitrogen, that's the solvent. So solid solutions exist when we mix metals and alloys. So if we think about a nickel, that is a solution, but it is a solid. So we have a 5-cent piece is made up of 25% nickel and 75% copper. And so because only 25% of it is nickel, that's going to be our solute because it's less than the 75% of copper, which is our solvent. And let's think about gold, which we're all familiar with. Gold is made up of 24 parts. So if you have 24 karat gold, it's pure gold. But if you have 14 karat gold, you have 14 parts of gold. and then the solvent is the solvent, and you have 10 parts of copper and silver. That's going to be your solute. So whatever you have more of is going to be the solvent, and what you have less of is going to be your solute. So we have 14 parts of gold solvent and 10 parts of the others. So there are some rules as to what makes a solution and what is going to be soluble, or what's going to dissolve into a solvent. So we have a rule that like dissolves like. Polar compounds dissolve in polar solvents, and nonpolar compounds dissolve in nonpolar solvents. So we can think about oil and water with this example. If you try to mix water, which is polar, with oil, which is nonpolar, the two won't mix. But if you mix another polar molecule in water, it will dissolve. And if you mix another, let's say fat, which is nonpolar, into oil, then it will mix as well. So when we think about chemistry, the most common liquid solvent is H2O, and solution and water are referred to as being aqueous. And so we saw this aqueous term in chapter 5 when we were talking about chemical reactions, and now it kind of makes sense. A lot of these reactions, especially those that occur in the human body, occur in aqueous or water-based environments. So we're going to talk about some solubility rules, and for preparation for exams and quizzes, I would just try to write these rules down and kind of commit them to memory. So we have ionic compounds are generally water soluble, but if the force of attraction between the ions in the compound are stronger than the attraction between the ions and water molecules, the compound will not dissolve. So we have a graphical or pictorial representation of this below. The particles of the solute will dissolve if it's more attracted to the solvent particles than to itself. So we have here this undissolved solute. The solute, which is what there's less of, is going to be here represented in the purple dots, and then the solvent particles are in the blue. And so you can see here that all the purple dots are together because they have more of an attraction with each other than they do the water. And so this is undissolved. However, if you do have more of an attraction between the solute and the solvent or water, then you will have a dissolved solute. So if you can see that all of these purple dots are no longer clustered together, they're actually dissolved and having forces of attraction with the water molecules. And so this is the difference on a molecular level between an undissolved and a dissolved solute, and kind of is the basis for the rules that we'll talk about in the next slide. So solubility rules are used to determine whether a compound dissolves or is soluble, or whether it precipitates as a solid, is insoluble. So whenever you think of insoluble, you have to think that there is a solid that is formed. And you can kind of think of it as if you had some water and then maybe some crystals at the bottom. That would be your solid, and that would be insoluble. So here are some rules for solubility of ionic compounds. Remember, ionic compounds are the ones that are between mostly a metal and a nonmetal. And it requires the one atom to donate electrons and the other one to take electrons. So the first rule is a compound is soluble if it contains one of the following cations. So cations are things that have a positive charge on them. So we have group 1 cations. These are going to be lithium, sodium, potassium, rubidium, and cesium. And then we have also, if the compound contains ammonium ion, which is NH4, then it'll be soluble. And we'll go over a few examples, but essentially you'll be given a compound and you'll be asked whether it'll be soluble or insoluble. Rule number 2 is a compound is soluble if it contains one of the following anions. Anions are those negative charged atoms. So group 7 anions are chlorine, bromine, and iodine, except if they're in compounds with silver, lead, and mercury. So if you were to see AgCl, even though it has the chlorine in it, because this silver is there, it's not going to be soluble. So this is one of the rules that has an exception. If the compound has nitrate in it, NO3 minus, it's also going to be soluble. If it has acetate in it, CH3, CO2 minus, it'll be soluble. And if it has a sulfate, it will also be soluble, except for compounds with Ba, lead, and mercury. So this is another one with the exception. Two of these show up in both. So if you were to see barium sulfate or BaSO4, that would not be soluble and it would give you a precipitate at the bottom. So let's do some examples of determining solubility. So we have this compound here, and the rule 1 says any compound with sodium will be soluble. So this compound is soluble because it has a salt, according to rule 1. Magnesium phosphate does not contain any of the ions that would be soluble, so it's insoluble. It doesn't contain any of those group 1 elements or the ammonia. Then we have KOH, and according to rule 1, it says any compound with potassium will be soluble. So the goal for this is to be able to look at a compound and predict whether it be soluble or insoluble. And anytime that you see insoluble, that means that we get a product, and that means that we have a precipitate or some residue that's formed in the bottom of our reaction. So what we really would like to do is to look at a chemical reaction, those like we looked at in chapter 5, and really be able to understand whether the products that we form are soluble or insoluble. So we have this equation up top where we have magnesium nitrate that is going to combine with NaCl or table salt, and that's going to give us magnesium chloride and sodium nitrate. And so if we look at rule number 2, we have magnesium chloride that's formed, and because we have that Cl, that's one of those anions, it's soluble. And according to rule 1 and 2, because we have a sodium and the nitrate, so I'll go back to that. We have the nitrate here and the sodium here, that's going to make this soluble. And what we need to be careful of is when we have soluble products, it actually isn't going to give us, there isn't, and a reaction isn't going to occur. We're not going to get a product. So the reaction should be written magnesium nitrate plus sodium chloride equals no reaction, because these two things are soluble, and so we wouldn't be able to pick them out in our solution. It would just look like water. And we know that there's water because this AQ means that it's aqueous. So let's do another example. And in this example, we're actually going to get a product. So we have lead nitrate plus sodium chloride. Let's look at our products and see whether they're soluble or insoluble. When the reaction occurs, it gives us silver chloride plus sodium nitrate. So let's look at rules 1 and 2. The sodium nitrate is going to be soluble because the sodium and the nitrate are two compounds that allow a compound to be soluble. And then rule 2, if we look back, we have silver chloride. And so even though the chlorine is here, which would make it soluble, we have this exception. So except for compounds with silver. So this product is actually going to be insoluble, and that means that we're going to get a product. So this reaction should be written with a subscript to identify the insoluble compound. So we know that these are going to be aqueous, we started with. We have the silver chloride that is insoluble, meaning it's going to be a solid, just like we talked about. Precipitates as a solid is insoluble. So we can put the solid here, S, plus the sodium nitrate aqueous. And because we get this solid product, we're going to have a reaction. So if you don't have two soluble factors, there's no reaction, but we do form this nice solid product. So this is what our reaction looks like. So now that we talked about what a solution is, and what a solute and a solvent is. Now we need to talk about how we define or characterize those solutions. And so we like to think about this in terms of concentration units. So we have a concentrated solution. That's a solution in which a large amount of solute is contained in a volume of solution. Or we can have a dilute solution, and that's a solution in which a small amount of solute is present. And so here we have another pictorial representation of what this looks like. So here we have a dilute solution. We have small amounts of this pink ball, which is the solute, and a ton of water here. Versus a concentrated solution where you can see that we have tons of the solute and the same amount of water, but now these solute molecules are more concentrated closer together, and there's just a lot more of them in the same amount of space. So we want to be able to represent this as a number. So we have different ways that we can express a concentration. We can have percent concentration, and at the end of this lecture, I'll show you there's a little cheat sheet that is on Moodle that will have all of these equations on how to calculate concentration in them. So we have the percent concentration. Percent means parts per 100. So you're going to have the parts of the solute divided by 100 parts of the solution. So these parts may be weight, which is grams, volume, which is liters, or a combination of the two. So we have three concentration units that we can use. We have weight over weight percent. So this is going to be the weight of the solute divided by the total weight of the solution times 100. So for example, let's say we had salt here as our solute, water as our solution, and then multiply that by 100, and that would be gram over gram. Then we can have a weight per volume percent. So that's the weight of the solute in grams, and then the total volume of the solution in mils. So we'll divide the weight of the solute by the total volume of the solution in mils, and then you're going to multiply that by 100%. And then the last one that we're going to have for percent concentration is volume by volume percent. So we'll have the volume of the solute, that'll be in mils, by the total volume of the solution times 100. So this will be pretty straightforward. You'll be given some numbers, and then you will plug them into the equation and figure out the percent concentration. So if we do some examples, if we want to determine the weight per weight percent of gold in 14 karat gold, we know that we have 14 parts of gold, as we talked about, and then the whole total, the solvent, will be 24 parts total. And then we'll multiply that by 100, and so that gives us 58%. Let's say we want to calculate the weight per volume percent concentration of a solution of 16 grams of sodium chloride dissolved in a total volume of 200 mils of solution. So we'll have 16 grams of sodium chloride, which we got from our example here, and we'll divide it by the solution, which is 200 mils, and we'll multiply that answer by 100, and that gives us 8%. So we have an 8% sodium chloride solution. And then next, we're going to have how many grams of potassium bromide are required to prepare 2.00 liters of a 2.85% potassium bromide solution. So here we're given the percent, we're given the volume, and it wants to know how many grams. So we're going to need to work with our equation. So we always want to work in mils, not liters. So first we're going to convert the 2.00 liters to mils. And this we should remember from earlier on in the semester where we did conversion factors. We know that in 1 liter we have 1,000 mils. And so 2.00 liters is converted to 2,000 mils. And then we would like to know the grams of potassium bromide. So let's plug this into our equation. We'll put 2.85% because that's the percentage we have been given. We want to know the grams of potassium bromide, so that's going to be our X. And then we have to divide that by the amount of solution that we were given multiplied by 100. And so when we solve this equation for X by multiplying both sides, that'll give us 57 grams of potassium bromide. So we have some more examples here. We have an antifreeze solution contains 896 mils of ethylene glycol and a total volume of 4 liters of solution. Now we're going to do the volume per volume. So we're given 896 mils and 4.00 liters. Again, we're going to work with mils rather than liters. So we have to convert the liters to milliliters. 1 liter equals 100 milliliters. So that gives us 4,000 mils. So we'll plug this into our equation. We'll put 896 mils of ethylene glycol divided by 4,000 mils of solution, multiply that by 100, and that gives us 22.4% ethylene glycol. So now we're going to do where we're given the percentage of volume per volume, and we want to know the volume of isopropyl alcohol that is needed to make 500 mils of solution. So we're going to put X mils of isopropyl alcohol divided by 500 mils of solution times 100 equals 70%. So this is our percent, and then we have the volume of the isopropyl divided by the volume of the solution. So if we just multiply by 500 on both sides, that'll give us that X mils is 350 mils of isopropyl alcohol. So you just need to solve for the variable X. Another concentration unit that we have is parts per million. You'll see this as ppm. This is used for extremely small concentrations. And so the parts per million equation is weight or volume of the solute. So for this, you can either work in grams or mils, divided by the weight or volume of the solution, and we'll multiply that by 10 to the 6. So now we're going to talk about molarity, and this is the most used concentration unit. You'll see this indicated by the big M. And what molarity is equals the moles of the solute and the liter of the solution. And so in chapter 5, we talked all about moles and atoms and how we can do a moles to gram conversion. So this is really great because we can look at moles of the solution and then figure out how many grams of solution there, solute there is. So to calculate, we'll say, what is the molarity of a solution containing 0.5 moles of solute and 250 mils of solution? So if we just plug in these numbers into our equation, we have the moles of solute. So we'll put 0.5 moles of solute here where we have moles of solute, and then we'll divide by 0.250 liters. Again, we have to convert this from mils to liters of solution. And when you divide 0.5 by 0.250 liters, that gives us a 2 molar solution. So how can we use molarity? We can use molarity to determine how many moles are present. So you could be given a molarity and then calculate the moles. So we're going to do that for calcium chloride, where we're asking how many moles of calcium chloride are present in 200 mils of 2.0 molar calcium chloride. So we're given the molarity of M, so we're going to plug this 2.0 molar into the M spot of this equation that's here. We want to solve for the moles, so we'll put X here. This is supposed to be calcium chloride. I apologize for the way it's showing up on the slide. And then we're going to divide that by the liters of the solution. So we're given 0.200 liters. So unlike the other equations where we wanted to work in mils, this you actually want to work in liters. Be very careful. This is liters of solution. So if you're given milliliters like you're given in this, you need to use conversion factors that we did earlier on in the semester to convert that to liters. So when you multiply each side by 0.200, 0.200, because we want to get this alone. When you multiply 0.200 by 2.0, you get 0.40 moles of calcium chloride. So let's do a few more practice problems. For this slide, we have how many grams of KClO3 are required to prepare 250 mils of 0.40 molar KClO3, which is perchlorate. So we have, we're given that we have 250 mils, and we're also given a molarity. And from this information, we can figure out how many moles we have, and then we can use the information that we learned in chapter 5 to figure out how many grams that we have. So we have, to set up our equation, we're going to put 0.40 moles on the left side. We'll have X moles of perchlorate, and because that's what we want to know, that's our unknown, and we'll divide it by 0.250 liters of solution. And so we'll just multiply by the 0.250 liters so that we can isolate the X. So we'll multiply this side by 0.250, the other side by 0.250, and we're left with 0.10 moles. So if you multiply 0.250 by 0.40, you'll get 0.10. And that leaves us with the moles of this molecule. Now we want to figure out the grams. And so we'll do our mole to gram conversion that we get from the periodic table. So you need to calculate the molar mass of potassium perchlorate, and you will come to 122.6. So we'll have to set up our equation where we have 0.10 moles, and we'll multiply it by the grams to mole conversion of 122.6 grams, and we'll divide it by the mole. And so we can cancel out the moles here, and we're left with grams. And when you multiply 0.10 by 122.6 grams, you get 12 grams. And so that's how you kind of combine everything that we've learned up to this point into one question. And now we can also do this with the percentage, so going from a percent solution to the molarity. So we'll use our percent solution equations that we learned in a few slides back. We know that we have 2.85% potassium bromide. And so, and we'll just say that we have 100 mils of solution. So we know that for this, we have grams per mil. So we have 2.85 grams of potassium bromide divided by 100 mils of solution times 100. And so then we're going to solve for moles since we know the grams. So we're given 2.85 grams of potassium bromide, and we'll multiply this by the mole to gram conversion from potassium bromide. So you have to calculate the molar mass for potassium bromide by taking the atomic mass of potassium and adding that to the atomic mass for bromine, and that'll give you 119 grams. So you want your moles on the top and your grams on the bottom. And so instead of multiplying, we're going to divide 2.85 grams divided by 119 grams. And when you are finished, you'll get 0.0239 moles of potassium bromide. And so we want to calculate the molarity. We're not there just yet. We have the moles, but luckily, if we have the moles and the liters of the solution, we can calculate the molarity. So let's plug it into that equation. So we know that we have 100 mils of solution because we were given that information right here. And if we convert that to liters, it's 0.100 liters of solution. And so we'll plug in the moles and the liters into our moles and liters equation for molarity. And that will give us 0.239 molar when we take 0.0239 and divide it by 0.100 liters. And so we'll have homework questions and we'll do a lot of practice on this as well. So now we need to talk about dilutions and what are they exactly? So dilutions occur when more solvent is added to the solution. And so therefore it makes it more dilute, but will still contain the same number of moles of solute because all we did was add more water. We didn't add any more solute. So here's an example of what a concentrated solution looks like. We have less water, and you can see that we have 7 molecules of water and 7 molecules in 200 mils of water. So this is pretty concentrated. You can see that the molecules are very close to each other. This is a dilute solution because now we've added 200 mils of water to the 200 mils of water that was already existing. So we still have the same 7 molecules, but now we have more water and there's more space in between the individual molecules. That means it's more dilute. So it's kind of like if you had a glass of really, really sweet iced tea. If you added more water to it, you can make it less sweet. And that's because the sugar becomes less concentrated. So when we do dilutions, we can calculate the change in the concentration or the change in the volume. So when more solvent is added, the solution becomes more dilute, and we'll use this equation below. We'll have M1V1 equals M2V2, where M is the molarity and V equals the volume. So M1, or the 1 in this, is going to be our starting molarity and our starting volume. So you can think of that as the starting amount of molecules and our starting volume here. And then we'll have the M2 or V2, which is going to be our final molarity and our final volume. So sometimes you'll see MI, which will be initial, and then you'll see M2, MF, or VF, which could be final. But for this purposes, we'll do M1, V1 equals M2, V2. So for an example, we have a 100 ml sample of 0.200 molar sucrose, and it was diluted to 500 mils, and we're going to calculate the new molarity. So these are our starting volume in mils and our starting molarity here. So we'll plug 0.200 M and 100 mils into the M1V1 side of the equation on the left. And then we want to know what the new molarity is, what the M2 is. So we have a question mark here because we don't know yet. And then we'll have 500 mils. That's our final volume that we were given. That's the V2 here. And so we want to solve for M. In order to do that, you need to divide by 500 mils on the right side, and also make sure you divide by 500 mils on the left. And so when you do that, you get left with M by itself. And when you multiply 0.200 by 100 and then divide that by the 500 mils, you get 0.0400 molar sucrose. So next we need to talk about solubility. So there is a limit to how much solute can be dissolved in a given amount of solvent. So you can think of it as, again, if I was adding salt to water, you can see that the salt can start to dissolve, but if you add too much salt, there's just simply not enough space for the water to accommodate all of the salt. So we like to talk about that in solubility. And the units of solubility is the grams of solute divided by 100 grams of solvent. So let's use our water and salt, sodium chloride example above. So let's say we have a beaker and it contains 100 grams of water, and then 50 grams of sodium chloride are added to it. What happens? the process of solution begins. So you have sodium chloride that's added to the water, and it begins to dissolve as sodium and chloride. So what happens is when we actually add the salt, it's no longer the sodium attracted to the chloride. You now have the molecule fall apart, and you have individual salt, sodium ions, and individual chlorine ions, because they are interacting with the water. And so if we can go back to this example here, you can think of it as this is the water and this is the salt. And so the sodium is going to be surrounded by water, and then the chlorine is going to be surrounded by water. So we have to think of them separately when we think of solubility. And so as the number of ions in the solution increases, the chances of the two ions coming into contact increases. When they come close enough, they will collide and stick together because they are attracted to one another. So now, instead of the sodium being by itself and the chlorine being by itself, now they've come into such close contact, they stick together and they form salt again. And so the solid salt will begin to precipitate, and that's called crystallization. And so that's when you add salt to water and you just see the salt at the bottom of the beaker. And so we call this saturated solution. And a saturated solution is a solution where the rate of ions dissolving equals the rate of crystallization. In this situation, the solvent holds as much solute as it possibly can, and the system is in equilibrium. So solubility is this concentration of solute in a saturated solution. So if we look at the solubility of sodium chloride, we have that it's 36 grams of sodium chloride for 100 grams of solution. So that's saying you can get 36 grams of sodium chloride, and we'll just say into 100 grams of water. So in our example before, we added 50 grams of sodium chloride to 100 grams of solution, but only 36 grams of the sodium chloride will dissolve. That's what we get from this solubility constant here. And so if you take 50 minus 36, the remaining 14 grams will be undissolved and will appear as a solid at the bottom of the container. So if only 30 grams of sodium chloride has been added, all 30 grams would dissolve because 30 is less than this 36, so there's enough room for it. The solution still has a capacity to hold 6 grams of sodium chloride. So this is unsaturated. So a saturated solution would be if we had 36 grams of sodium chloride, because that 36 would equal this 36. When you have things crashing out of solution or precipitating, it's because you have way too much. So 50 is more than 36, so there's going to be some extra. In this example, we have less than it, so it's unsaturated. So how can we manipulate the solubility? And some of you have done this if you are heating water and you want sugar to dissolve. So for ionic and covalent solids, increasing the temperature will increase the solubility because we will give the ions or molecules more energy to move around and interact with the solvent. So we make things warmer, there's more molecular motion, things are moving around, and they're more likely to interact with the water instead of interacting with other solute molecules. For gases, if you increase the temperature, will decrease the solubility because the added heat will allow gas molecules to escape to the gas phase instead of staying dissolved. So in order to go from a liquid to a gas, we need to heat up a solution. And this happens like when you boil water on the stove, you'll see steam. So if you increase the temperature, you'll actually have more of that transition from the liquid to the gas phase, and that decreases solubility. For gases, increasing the pressure will increase the solubility because the increased pressure will force molecules together such that they can be trapped in the liquid. So if you think of like a balloon applying pressure on the air that's inside of it, the more pressure that you add, it will force the molecules together. So if we force the molecules together, then they can interact with the liquid more than they can, again, with other solute molecules. So we call this colligative properties. solubility can affect boiling and freezing points of a solution. When ions or molecules are dissolved in a solvent, they get in the way of solvent molecules being able to interact with each other. So we have boiling. This is when molecules move from the liquid phase to the gas phase. That's like if you put, again, water on the stove and boil it. To do this, they must overcome any attractive forces that keep them in the liquid phase. If ions are present, they are attracted to the water molecules and prevent them from exiting to the gas phase. So we can prevent things from going from the liquid to a gas. We're going to call this boiling point elevation. We have something on the opposite, which is freezing. And this is when molecules come together in an ordered fashion to become a solid. And we do this when we put water into ice cube trays and then pop it in the freezer. We go from a liquid to a solid. And to do this, we need to slow down all those attractive forces so that they can interact with each other and form more of an ordered structure like we see in an ice cube. If ions are present, they prevent the molecules from coming together, and that we call freezing point depression. So here is a picture of what can be happening. If we have on our left system A, the liquid particles are able to easily escape the liquid form, so that's here in the bottom, and when we heat it up, the boiling now allows these molecules to be in a gaseous form. However, if we add, let's say, salt into the liquid, now we're going to have some interactions between these green solutes and the salt, and that's going to prevent these molecules from moving from the liquid to the gas phase. And so now, in order to get the liquid to go into the gas phase, we actually have to heat this up. And so you can see this here on the graph. If you have temperature here and you increase the temperature, you can have more of this vapor in solution, and that can also happen with pressure. And now we're going to talk about freezing point depression. So here on the left, we have system A. So the particles in the solid can easily shift into the liquid phase at the normal freezing temperature as shown. And that's because these molecules are able to slow down and form a structure and interact with each other, which is what we need for things to go from a liquid to a solid phase. However, in system B, which is on our right, the particles in this solid cannot shift into the liquid phase at normal freezing point temperature because solute particles block movement from the solid phase to liquid phase. So this is going from a solid to a liquid. And if you have, let's say, these little molecules, they're preventing the molecular motion that was allowed here. So actually, I'll correct myself. I'm sorry. This is when you're trying to go from a solid to a liquid. And these molecules can freely leave the solid into the liquid phase because nothing's really holding them. There's no attractive forces that are holding them together. However, in system B, you have these little red molecules and solutes that's been added. And so this is essentially blocking or preventing the molecules moving from the solid to the liquid. And so we can use equations to calculate the magnitude of changes in the boiling and freezing. And for this, for the purposes of our lecture, you just need to know or have access to these equations here. One is the boiling point elevation, and the other is the freezing point, it should say depression here. These little constants here, the delta equals change. So this is going to be changes in the boiling and the melting point. Melting is the opposite of freezing, so it's when we go from a solid to a liquid, and boiling is when we go from a liquid to a gas phase. This K of B and KF, they're constants for the solvent, and so you can get these from some textbooks. There are manuals that have the constants that are already been figured out. And then M is going to represent the molarity. And here the M is moles of solute over kilograms of the solvent. And so a question that you might get on a quiz or an exam is you would be given some of these factors like the KB and the M, and you'll get asked to calculate the delta TB. So that is all that we have for today. And a few of you have asked about some extra credit, and I'll post this on the Moodle page as well. But for extra credit, I will have you complete the homework questions for chapter number 8. A lot of the material is just knowing the equations and plugging in the information that you're given. So the more practice that you have with doing that, the more successful you'll be in handling the material. So I will put this announcement on the Moodle page for anyone who's interested. Please complete the homework 8 questions. They are posted on the Moodle site, which I can show you. Okay, so here we have the Moodle site for Chemistry 121. You'll find today's lecture here in the Spring 2020 online lectures, and I will also put a few YouTube videos up that might help explain solutions, solutes, and solvents a bit better. And then for the homework problems, you'll do chapter 8 here, and you only have to be responsible for the questions that are circled here. So there are a few here that are circled, and you can complete those. And when you're all finished, you can either, if you have access to scanning, but if you simply just want to take a picture of the completed assignment with your phone and then email me that, you can get some extra credit points. Okay, so again, next week we'll have a quiz on chapter 5, and we'll continue on. We won't be doing chapter 9, I believe, because the semester is almost over, so we'll go right to chapter 6 where we'll talk about acids and base. And for anyone who needs any additional help, again, there'll be office hours tomorrow via Zoom. I've sent the information out, and that starts at 1 p.m. I hope you all have a good day. Bye.